Welcome back to I Can Science That. Here's a topic I've wanted to touch on for some time now. This is something that comes up in a lot of different discussions that go on in this channel. Let's talk about reference frames. What exactly is a reference frame? What do we mean by that when we say it? And how can a better understanding of reference frames help us with these conversations that we're having? Okay, so let's start off with let's define it. What is a reference frame? A reference frame is nothing more than a coordinate axis. That's all it really is. Here we have, just like you would have done in math class in high school, you've got an x-axis, you've got a y-axis. These are just lines on paper. You just draw these things, and then you can locate a point. Right? You can locate a point on your axis, and then you can tell everybody, where is this? Like, this is 3, 4 or something like that, right? You would just say that's how we describe a location by giving the coordinates of it. And the coordinates have to be on some kind of axis. If we didn't have the axis, then the coordinates wouldn't make any sense. It's like saying, hey, where's your kitchen? Where's your kitchen? Well, my kitchen is 10. Kitchen is at 10. 10 what? 10, what does it mean? Right? Any position, any location, anywhere in the world, we have to describe it in terms of some other location. You can't just say, like, my kitchen is at 10. Makes no sense. But I could say, my kitchen is 10 meters north of my living room, right? Something like that. That makes sense. Like, if I know where the living room is, then I know where the kitchen is, because I have, like directions from one to the other. And that is what a reference frame is. A reference frame is this location that we'll agree on. We'll agree that that's where that is. And then we can give coordinates of any other point relative to that original location. And to do that, we'll need the location, and we'll also need the orientation. Which way does the x-axis point? Which way does the y-axis point? And once we've agreed on that, we have what's called a reference frame. We can also do this in 3D. It's easier to draw in 2D, so we'll do most everything in 2D. But you could draw it in 3D, or you could do it in a real three-dimensional world like we live in, just by giving a third coordinate. So that's all a reference frame is. Now let's talk about some examples of how we use it in these conversations and how people misunderstand what it means in these conversations. All right, let's take your classic passenger on a train example. We have here 3 obvious reference frames. We have your ground. The train is rolling along the ground, and then we have a passenger. Maybe the passenger is walking on the train. Okay, so we have a ground reference frame. We could say, we're going to need to pin it at some position on the ground and agree what that means. So, like, maybe that's the next station you're pulling into. That's the let's say the Mission Street station, right? There's a Mission Street station, and that's where we'll put this coordinate system. And then we'll have one for the train, let's say right at this wheel of the train, or maybe that's where the engineer sits, the bottom of the engineer's chair. We'll lock, that's going to be our axis, our coordinate system for the train. And how about we got a passenger, so we'll just pin it to the passenger, somewhere on the passenger. I got it like on his shoulders, because I thought that looked good in the diagram. So like right here in the middle of your chest, we'll put a reference frame. That's your reference frame. So the question becomes, I have a passenger walking along the train. I have the train rolling along the tracks. Which reference frame is the passenger in? Is the passenger in A, the ground reference frame? The ground is what's really real. The passenger is really in the ground reference frame. Or, no, the passenger is walking along the train. So the passenger must be in the train's reference frame, because the train is moving different from the ground. Or maybe the passenger is in the passenger reference frame. That's the reference frame attached to the passenger, so the passenger is in the passenger reference frame. Or D, none of those. So pause it. Let's pause the video and maybe type down in the comments, what is your answer? What do you think the correct answer? I should always say what is the most correct answer, and why do you think that is? Let me give you 5 seconds here. We'll count down. 5, 4, 3, 2, 1. Let's unpause. The correct answer is D, none of those. No. Explanation. Remember, what is a reference frame? A reference frame is nothing more than a coordinate axis. So it doesn't make any sense to say the passenger is in a coordinate axis. The passenger is not a mathematical number. The passenger is a person. The passenger is an object, right? And objects are not physically attached to reference frames. That's not what a reference frame is. A reference frame is just a coordinate axis. We can choose to work with the passenger's location. The position of the passenger can be described in any reference frame that we wish. Whatever is convenient for us at the time, that's perfectly valid. But what's not valid is to say that the passenger physically exists in or is attached to a reference frame. The reference frame is not a physical thing. A reference frame is just a construct that we agree on. So the passenger is not in any reference frame. We could describe the passenger's position in terms of whatever reference frame we want, but if we want to communicate, we'll have to be clear which reference frame we're describing, right? So if I say the passenger is currently 10 meters north, 10 meters north of what? 10 meters north of the train's reference frame, which is right here, or maybe is the passenger 10 meters north of this ground station that we've marked. Certainly he's not 10 meters north of himself. That seems silly, right? So where is the passenger? The passenger is at 0 meters from himself. No surprise there. He is some number of meters from the front of the train, and he's some other number of meters from the ground reference station. All of those perfectly valid. Let's do a little example with some numbers. A classic word problem type of setup. We'll have our little passenger. Our little passenger is on the train, walking eastbound at about 1 meter per second. The train is cruising along westbound at 25 meters per second. The ground reference is here at a station, and I'm going to put the train's reference coordinate system, right here. Let's say that goes right through the engineer's seat. Okay, currently the train is 200 meters east of the station, and the passenger is currently, let's say, 30 meters east of the engineer's seat. Obviously not to scale. So how could we describe the passenger's current location in each of these 3 reference frames? So let's say the passenger's location in the passenger's reference frame. Well, that's 0, right? That's 0. The passenger is sitting right on his own axis. So we'll say that's 0 meters. He's at 0 meters. Where is the passenger in the train's reference frame? So the passenger is here, train is there. We said that was 30 meters. So the passenger's location in the train reference frame is 30 meters east, right? Okay, last one is in the ground reference frame. Where is the passenger currently in the ground reference frame? Well, we said this is 30 and this is 200. So together, from here to here, that's 230, 230. So in the ground reference frame, the passenger is at 230 meters. So again, which reference frame is the passenger in? That's a nonsensical question. Where is the passenger in each reference frame? That we can say. Where is the passenger in the ground reference frame? 230 meters. That we can say. Is the passenger in the ground reference frame? That doesn't make any sense, right? It's not a physical connection. Okay, let's do velocities now, because we're gonna ease into relativity with this, and so we need to talk about not just positions but velocities. What is the passenger's speed or velocity? We're going to do one dimension, so we'll call it velocity. But we mean the speed in the eastbound direction, right? What is the passenger's speed in any direction, really? In his own reference frame, of course, that's 0, because the reference frame of the passenger, we attached it to the passenger, and so he's not moving compared to himself. I mean, obviously. So in the passenger's reference frame, the velocity is 0. What about the train's reference frame? Again, the train is going westbound at 25. The passenger is going eastbound on the train at 1 meter per second. So compared to this purple reference frame, what is the passenger doing? Remember, the purple reference frame, we've said, is the location of the train. And if the train is moving, the reference frame, that axis, that purple axis, is moving with the train. It's going to follow the train as the train moves, just like the blue axis follows the passenger as the passenger moves. So what is the speed of the passenger in the coordinate system of the train? We should get 1 meter per second. 1 meter per second, and it's eastbound. Compared to the train, the passenger is moving east at 1 meter per second. That's this line right here, and that is what it means. It means in the reference frame that we have attached to the train, the passenger is moving eastbound at 1 meter per second. Now, does that mean he's literally moving 1 meter per second? Well, I mean, all velocities must be relative to something. Relative to the train, yes, he's literally moving at 1 meter per second compared to the train. But the train itself, we said, was going westbound compared to the ground. And so what is the passenger's velocity compared to the ground? And for that, we should get 24 meters per second, and it's now westbound. There's 25 meters per second that the train is going west, and 1 meter per second that the passenger is going east. And so compared to this axis, which is stuck at the station, the passenger is getting closer to the station at the rate of 24 meters per second. This is the train itself, right, getting closer to the station at 25, but the passenger is walking away at 1 meter per second. So once again, let me say it one more time. What reference frame is the passenger in? That doesn't make any sense. That's not a question that makes sense. You could say, what is the speed of the passenger in the reference frame of the train? That we could say, and here it is. It's 1 meter per second. So now let's do another example, the classic helicopter example. And this is where a misunderstanding, misapplication of the concept of reference frames can lead you to the wrong conclusion about what's physically happening. Now that we understand what a reference frame literally means, let's see if we can get the correct answer to this logical puzzle. So here we go. We have a helicopter sitting on the ground, sitting on the helipad, just sitting there, and the Earth is rotating eastbound at 1,000 miles per hour. So, presumably we're very close to the equator. So the Earth is spinning and it's rotating eastbound at 1,000 miles per hour. Question: what reference frame is the helicopter in right now? While the helicopter is sitting on the pad on the ground, what reference frame is the helicopter in, and the follow-up then, how fast is the helicopter moving? Okay, so like maybe pause it, jot down your comments. What are your answers to these two questions? And then let's do the follow-up. What happens now? Now the helicopter takes off straight up and just hovers straight up over the helicopter pad. It's going to sit there, take off. We're now not touching the ground anymore. Not touching the ground. We're hovering over the ground. What reference frame is the helicopter in now? And how fast is the helicopter moving? So jump down into the comments and let me know if you have answers to those questions. And let me remind you, maybe go back a slide or two. What is a reference frame? So how do I answer these questions? So moving on from there, let's talk orbital mechanics. And for this, I thought about like drawing these diagrams myself and so forth, but instead, let me just take us to the URL here that's on your screen, and it should be linked down in the doobly-doo. Okay, here we are. So there's that web page. It talks about what a reference frame is. It talks about something we're going to get into in a future video is the difference between what is an inertial reference frame and what is a non-inertial reference frame. We'll see this right here. And it talks about an inertial reference frame is not accelerating. And this is something that there's been some confusion with certain people that I've interacted in the past here with on the channel. I just wanted to point out right here, an inertial reference frame has no rotation. You cannot have, there can be absolutely no acceleration, including rotation. That means if you're in an inertial reference frame, you are not rotating. Okay? Just so that's clear. Okay, and so then I wanted to skip down to two of the very frequently used reference frames that we'll see in orbital mechanics, in GPS measurements, that sort of thing. You'll hear about the Earth-centered inertial, or ECI, reference frame. What does that mean? That means that we're going to put the axis at the center of the Earth. So the axis right here, you can see it. The axis is right at the center of the Earth. And remember, in the global model, which just clearly is, the Earth is rotating. But a rotating Earth would not be inertial. So the Earth-centered inertial reference frame is one that does not rotate. So that means that this x-axis that we currently have poking out through, through Africa there, would not stay on Africa. If it is inertial, it does not rotate with the Earth. It's just stuck to the Earth there. The Earth would rotate, and that axis would point out towards a fixed star. Right? In the stars are not rotating around us. Obviously, the Earth is rotating. And where does it point? You can see here the x-axis points towards the March equinox. That's where we'll decide to point that. And then the z-axis, we're going to point it up towards Polaris, literally to the celestial North Pole. So that's what that axis is. And that's useful for doing orbital mechanics because a satellite going around the Earth is not attached to the Earth, and there's no atmosphere to speak of up there. So the atmosphere, whatever the atmosphere is doing, isn't going to influence that at all. So the dominant forces then are just gravity, and the centripetal force needed to do an orbit is going to be gravity. And that's it. And so we can basically imagine the Earth now as just a point mass that doesn't we don't care if it rotates or not. It's just a point mass, right? Just a point mass, and we can do orbits around that, and we can give all of our coordinates then in this Earth-centered inertial coordinate system and do all of our satellite math. It's very simple. And then you might want to ask, well, where is that over the Earth? And then you'll need to bring the Earth into the Earth-centered inertial, where you'll find the Earth is rotating in the Earth-centered inertial reference frame. You have to do that conversion. Okay, what's the other one? The Earth-centered, Earth-fixed, or ECEF reference frame is one that is, again, centered on the Earth. So we're going to center it just like we did before, where we're going to put, the z-axis going right through the celestial North Pole. But now the x-axis is going to be attached, it should say here, usually to there we go. The x-axis is going to be attached to the prime meridian. So we're going to go right through, the Greenwich meridian on Earth. So this coordinate system stays on the Earth, and it also rotates. It rotates at 15 degrees per hour, so to speak, right? That it rotates with the Earth. That means this is a non-inertial reference frame. So this is a useful reference frame because this is the reference frame that sort of we live on, right? This is where you want to say, where is that satellite over the Earth? It's some country, some city over the Earth, and that's going to be attached to the Earth, which is doing this. So that's why this is super useful to describe where we are on the surface of the Earth. So if we're talking about a satellite, we're going to do our satellite mechanics in the ECI reference frame, and then we'll have to convert it down into the ECEF so that we can talk about where we are over the surface of the Earth. Okay, and those are those two very, very commonly seen. You'll see those acronyms, and sometimes people won't even tell you what that means. They'll say, oh, in the ECI, my coordinates are blah, 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 and I'm in the ECEF reference frame, the coordinates are, what is this ECEF? That's what that means. And let me point out, because there's going to be some keyboard warriors down there already banging it out. The ECI, inertial reference frame, supposedly attached to the Earth, that would only be true if we're in a geocentric solar system, right? That's only inertial in a geocentric solar system, right? Because the Earth is supposedly going in a circle around the sun. And you bet, right? We're going to work for Earth-bound satellites. Satellites, man-made satellites around the Earth. That's fine. The difference created between an Earth-centered coordinate system and one that's centered on the solar system is so small that it's negligible. And we could get into orbital mechanics. I keep thinking maybe I'll make an orbital mechanics crash course where we'll cover exactly what forces make an orbit happen. And one of the fallouts of that is that when you're in orbit, there are no net forces acting on you, right? So you see that in footage from space, from those astronauts up on the ISS or whatever. They're in 0G, or we say microgravity. They're not away from the gravity of the Earth. The gravity is still there. It's just they're falling, and those balance to zero, so we don't feel anything. And that same is true of us going around the sun. So we don't feel anything from that. And you're like, oh yeah, but we're rotating. It's got to be the x acceleration. Well, the accelerations are balanced. So it's nothing. So it's just going to cancel right on out. So that's why we can get away with calling this Earth-centered inertial reference frame inertial. It's inertial enough to do these calculations and have it not matter. And then, there's a further debate that we could talk about in a heliocentric model. How inertial is this? Is this still inertial or not? And in what context is it still inertial? That's another topic. We can go there. Okay, so hopefully the keyboard warriors will enjoy that conversation. And so at last, let's summarize. What is a reference frame? As we've discussed, a A reference frame is nothing more than a coordinate axis. It's just a mathematical construct. It is not a physical thing. So objects, therefore, are not literally in a reference frame. That's just not even a thing. The reference frame is not a property of the object. I don't attach to different reference frames. In case you didn't get this answer already, the helicopter does not attach to the ground reference frame and detach from the ground reference frame, and now it's in a different reference frame because it left the ground. That doesn't make any sense. Instead, we can use any reference frame we choose. We could say, consider the helicopter in the ECEF reference frame attached to the ground. It's in the ground reference frame. And then it takes off. We can still describe the helicopter and its new location in the ground reference frame. We can do that. And maybe we're going to say, now that it's up and flying, it will make more sense for us to describe it in the air reference frame. We'll create a reference frame that represents the current prevailing winds in this location. And we'll put a reference frame on those winds. And we'll talk about the helicopter's airspeed. The airspeed is in the wind reference frame, and the ground speed is in the ground reference frame. They're both real numbers. It's just which one we describe. That's all a reference frame is. And finally, reference frames do not cause objects to move. There's no way that we could just simply by describing a helicopter in a different reference frame, that we could cause that helicopter to change direction and accelerate away from us. We could choose an accelerating reference frame in which we get an acceleration number, but that doesn't physically affect the helicopter. Nobody in that helicopter is going to see what we're doing with the math. Remember, this is just a mathematical construct. A reference frame is just how we choose to describe the position and the velocity of an object. It does not affect the object itself in any way. Okay, so hopefully we found that interesting, and there'll be lots of lively discussion down there. Planning to try to find some time to do a few more follow-ups. Maybe we'll talk about orbits. Maybe we'll talk about some geocentrism. And in order to have those conversations, I just wanted to have this basic groundwork that we all know what a reference frame is, because that's a term that's going to come up a lot. We're going to talk about that in what is inertia. We're going to talk about that in relativity. We're going to talk about that in special relativity, general relativity, Galilean relativity. You're going to talk about that in just these simple examples of, are helicopters going to fly away because they left the ground's reference frame? How do I understand what that means? Hopefully this basic foundation provides a stable place where we can move forward and have lots of deep conversations about more interesting topics. So please do, as always, jump down in those comments. Tell me what you think. Give me the answers to these questions that you thought. And let's start some lively but friendly and respectful conversations about these. All viewpoints are absolutely welcome. And let's be respectful of each other's views, okay? We can disagree and we can discuss. And maybe if we're respectful, we can get somewhere constructive with these conversations. All right, see you next time.